Hey guys, welcome back to my YouTube channel. So if you haven't yet, hit that subscribe button and turn on your post notifications so that you know every time I post a new video. Hey guys, welcome back to my YouTube channel. So last week one of you sent me the 2020 paper and asked me to go through it. So that's what I'm going to do, and also look out this week or next week for the 2020 Communication Studies paper, as well as the 2018 chemistry paper. Okay, so let's get into it. Let me not waste any more time. You know, I like to talk. So the first question says, which isotopic half-life is best suited for use as a tracer in medicine? A, 15 hours, B, 0.16 years, C, 5.7 times 10 to the 3 years, which is about, you know, let me write it, 5,700 years, or 1.4 times 10 to the 10 years, and that's even larger than 10 to the 3. So for tracers in medicine, you want something that will last a couple hours, but you don't want to choose something that will only last for a couple minutes, because you need the thing to run through the body and actually get to the point where you need to see. So in cases of blockages in the body, what will happen is the tracer will enter the body, you know, by however means or whatever means, you know, the doctor puts it in there, and it will accumulate at the blockage, right? And under an MRI or a CAT scan, then it will be able to be seen. So you want something that lasts a couple hours, but not years. That's too long. So number one, the most suitable answer would be A. Number two, which of the following factors is important in determining the stability of an isotope? And by now we should know that's the neutron to proton ratio. So whichever one of the answers, A, B, or C, or D, says that that's your answer, and it looks like C to me, so it's the neutron to proton ratio. Now, item 3 refers to the data in the following table, and this will require us to work out the relative isotopic mass based on the abundance given and the atomic masses given. Okay, there's so many ways in which you can work this out, and I'm going to do my favorite way first, and then I'm going to show you 2 other methods you can use. Alright, they're all the same, but it would be easy for those who are better able, or it would be easier for to understand for those who are better able to manipulate numbers. So alright, so the relative isotopic mass rather is equal to, let's say, 204 times 1.4%, which is 0.014, plus 206 multiplied by 24.1%, which is 0.241. You want to add that to 207 times 22.1, which is 0.221, and add that to 208 multiplied by 52.4%, which is the same as 0.52.4. Now put that into your calculator and see what you get. I wrote this wrong. 0.524, not 0.4. So 0.524. So put everything into your calculator and see the answer that you get. And I got 207.241. and that would be your relative atomic mass. Now another way you could write this is 204 multiplied by 1.4 over 100 plus 206 times 24.1 over 100. That plus, I apologize, let me do something, and hopefully I'll stop writing hill and gully. Chances are I won't, but it's worth a try. Alright, let me not erase anything, let me just continue. 207 times 22.1 over 100, and add that to 208 times 52.4 over 100. And if you put that into your calculator, you'll get the same answer. There you go. And you can also write 204 times 1.4 plus 206 times 24.1 plus 207 times 22.1 plus 208 times 52.4, and put this entire thing over 100. Delete. Just delete that. And let's do this. Great. So I'm gonna use the ruler for this. Great. And over 100. Anyways, we had deduced that the answer is 207.241. So looking for 207.241 atomic mass units, you will see that 207.24 is your most suitable answer. Now, number 4. Which of the following solids has a giant molecular lattice? Alright, off the bat, it's silicon dioxide. It is a giant molecular structure. Number 5, items 5 to 6. Items 5 to 6 refers to the half equations for the reaction between iodine and sodium thiosulfate. Now, the overall balanced chemical equation for the reaction is... Okay, so for a question like this, the first thing you want to do is look at the number of electrons and ensure that for both equations you have, if you have electrons on the left side, like for example over here, you want to ensure that for your next equation you have the electrons on the right instead of the left. If it's a case where you have both on the right or both on the left, all you have to do is flip one of the equations. Okay, so after you have established that, seeing that I have the same number of electrons here that I have here, I don't have to do any multiplication. So what I'll do is simply just cross them out. Now you just want to rewrite your full equation, and what I would get is 2s2O3, 2 minus in its aqueous state of course, plus I2 in its aqueous state yields S4O6, 2 minus its aqueous state, plus 2I minus in its aqueous state. Now you can check if the equation is balanced, and it seems to be, as well as if the charges are balanced. Now 2 times 2 minus is minus 4, and 2 minus here and another minus 2 here will give you minus 4. So the charges are also balanced. So you're looking for an equation that resembles this one. Now looking, as I said previously, I hope you wrote down the equation. The one that resembles what we just worked out is C. And that should be good for you. Now let's move to number 6. Number 6 says the oxidizing agent is. Now in the equation, the oxidizing agent would be the reagent or the reactant that's reduced, or the agent that's reduced. So you want to look at the equations and see which one is reduced. So if you look at I2 here, the oxidation state is 0, and here you have I minus, and now over here it is minus 2. So off the bat you can see that 0 to 2 it decreases, therefore this is reduced. But to be sure, I'll show you as per the sulfur in these two equations, or in the thiosulfate ions. So let's say the first ion you have S2O3 2 minus. So you can say 2S plus minus 2 times 3 is equal to minus 2. 2 threes is 6, so minus 6. Alright, so 2S minus 6 basically is what we'll have, is equal to minus 2. Therefore 2S would be equal to minus 2 plus 6, which would be 2S being equal to 4, and you divide by 2 on both sides to get S, and S is equal to 2. Now in the S4O6 2 minus ion, what you would see is 4S plus minus 2 times 6, which would give you minus 12, being equal to minus 2. And let's just do that. I'm doing a lot of shorthand work. So 4S is equal to 2 minus 12, or 12 minus 2, sorry. And what you would see for that is 10 over 4, which is 2.5. So it increases from 2 to 2.5. Therefore, it is oxidized. So the reducing agent would be I2. The oxidizing agent is I2. And if you were asked what the reducing agent was, the reducing agent would be the one that is oxidized, so the thiosulfate ion. Number 7. The ionic equation for the reaction of magnesium with hydrochloric acid is as follows, where the H plus represents the acid. Now the molar volume of the gas at RTP is 24 dm cube. So the volume of gas produced when 1.2 grams of magnesium reacts with HCl at RTP is, and let's get to working that out. Okay, so the first thing you want to do when working out a question like this is actually understand what it is saying and what it is asking you to calculate. So now we know the ionic equation, we know the mole ratios, we know the volume of gas produced at RTP, and we know how many grams of magnesium was used. Now we used 1.2 grams of magnesium, so we need to know how many moles this is. So basically 24 grams of magnesium is equal to 1 mole. So 1.2 gram will be equal to some amount of moles of magnesium solid. Now, what you want to do is cross multiply. So what you'd get is 24 grams times some amount of moles of magnesium, that's our unknown, being equal to 1.2 grams times 1 mole. Now, in order to get number of moles on one side, we want to divide through on both sides by 24 grams. In the end, 24 grams will cancel 24 grams, and grams here will cancel grams here. So you'd be left with the number of moles of magnesium being equal to 1.2 moles over 24. That would leave you with 0.05 moles. Now we know that we need to see the mole ratio between magnesium that reacts and what the hydrogen gas produced. Now, seeing that 1 mole of magnesium reacts and 1 mole of hydrogen gas is produced, you will see that it's a 1-to-1 mole ratio. So if 1 mole of magnesium reacts to form or to produce 1 mole of H2 gas, then 0.05 moles of magnesium will react to form 0.05 moles of H2 gas. So with that known, we know that 1 mole of a gas at RTP is 24 decimeter cube. So how much, or what would be the volume at 0.05 moles? All you have to do is multiply, because we'll be 24 decimeter cube multiplied by 0.05 moles being equal to X times 1 mole, divide through by 1 mole on both sides. This isn't necessary, but it's just to help you see what's happening. And what will happen is 1 mole cancels 1 mole, so we're left with X being equal to the moles cancel moles on this side. So 24 times 0.05, which is 1.2, and we're left with the unit decimeter cube. Alright, so that's equal to 1.2 decimeter cube. So the answer for this would be A. Okay, I hope that was clear. Now, number 8, when 86 grams of an ionic salt, calcium sulfate, dot some amount of water, so dot XH2O, is heated so that all of its water of crystallization is driven off, and 68 grams of calcium sulfate remains, what is the value of X is? So yeah, what is the value of X? Alright, this is how you'd go about working out a question like this. You want to write out an equation first and foremost. So what you'd have is CaSO4, which is calcium sulfate, dot XH2O yields, or yeah, CaSO4 plus XH2O. Now, what do we know? We started out with 86 grams and was left with 68 grams, right? And we are not sure how much water, but based on the law of proportion, you have to have the same amount of reactants and products. So what you're going to do is subtract 68 from 86, and that would give you 18 grams. Now, it's easy for you to look at it and say, oh, this is 1 mole, but that's true. 18 grams is 1 mole, but what you're looking for is the mole ratio. So what you want to do after this is actually find the relative molecular mass of calcium sulfate. And that should be fairly easy. What you're going to do, calcium 40 plus S, sulfur 32, plus oxygen, you have 4, so 4 times 16. And that should give you 40 plus 32 plus 4 times 16, 136 grams. Right? Now, what you want to do is find out how many moles would be in 68 grams. Right? Seeing that you already know that 18 grams of water would give you 1 mole. Now you need to find the amount of moles of calcium sulfate. So you know that 1 mole is equal to 136 grams. So some amount of moles would be equal to 68 grams. Right? You would end up getting 136 times the number of moles you need to find times 68. So divide by 136 and you should get a half, which is the same as 0.5. So the mole ratio that we would get is 0.5 moles of calcium sulfate to 1 mole of water. So what we really need is how much would 1 mole of calcium sulfate to water be. So 1 mole, and you can cross multiply and you would end up with 2 moles of H2O. So the water of crystallization for this would be CaSO4 dot 2H2O. So yes, the answer for the question, the value of X is 2. So the answer for this would be, or number 8 would be B. Number 9, which of the following criteria should be considered when accepting scientific theory? Now, this is the first objective in your syllabus. So experiments should be replicable. 2, data collected should be accurate and reliable. And 3, theories should show congruence between evidence and theoretical constructs. All 3. Deviations from ideal gas behavior generally occurs under conditions of. No, and the conditions for an ideal gas, or the conditions for a real gas to behave like an ideal gas, it would have to be at high temperature and low pressure. So deviations would be high pressure and low temperature. So that's what you're looking for, and that would be C. Number 11. Which of the following represents a pi bond? A pi bond is when 2 p orbitals overlap laterally. So, or side by side, if you want to say it like that. So, like this. Or could be horizontally, like this. Or like this. Whichever way. But here, 11 is C. Which of the following statements are true regarding factors affecting ionization energy? We're looking for the ones that are true. So, an increasing shielding effect decreases the ionization energy. That is true. Increasing shielding effects move the valence electrons further and further away from the positively charged nucleus, which weakens the force of attraction between the negative electrons and, the positively charged nucleus. So it makes it easier to remove electrons because less energy will be required to remove those electrons, the valence electrons, that is. Now, an increase in the size of the positive nuclear charge decreases ionization energy. That is true as well. An increase in the distance of the electrons to be removed from the nucleus decreases the ionization energy. That's also true. Hold on. An increase in the size of the nuclear charge would increase the ionization energy. So that's not true. No, if you are increasing the size of the positive nuclear charge, that is making the charge here, the positive charge, greater, then the amount of energy required to remove the electrons from the valence electrons would be more. Therefore, the ionization energy would increase rather than decrease. So that's not true. So the ones that are true are 1 and 3, which is B. Number 13. Which of the following processes represents an oxidation? Now you need to work out the oxidation state of manganese in all of these. So let's do MnO2 first. So 1 Mn plus minus 2 times 2, because there are 2 oxygens, is equal to 0 because there's no charge on this entire thing. And so you would end up with minus 2 is equal to minus 4, is equal to 0. So Mn is, in this case, would be plus 4. If you move this over to here, you get Mn plus is equal to plus 4. And it is then changed to minus 2. Therefore, this is reduced and not oxidized. We're looking for the one that is oxidized. Okay, so let's work out Mn in this. So MnO4, Mn plus minus 2 times 4 is equal to, this has a charge, so minus 1. And 2 4 is 8, so that gives you minus 8 is equal to minus 1. So Mn minus 8 is equal to minus 1, which would give you plus 7 being equal to Mn. You can do the long version to figure this out. So plus 7 and this Mn here, MnO, and 2 minus, work it out. Eventually, I don't think we're going to have to keep working out because the thingies will repeat. The compounds will repeat, the ions will repeat. So Mn plus minus 2 times 4 is equal to minus 2. 2 4 is 8, minus 8. Mn is equal to minus 2. So this would be 8 minus 2, which would be 6. So here it is 6 plus 6. So plus 7 to plus 6. This is also reduced. Okay? Bruh, behave yourself. Alright, now MnO2, we already worked that out and we got plus 4. And MnO4 minus, we got plus 7. So this goes from plus 4 to plus 7, so it increases, therefore it is oxidized. But MnO4 minus plus 7, MnO2 plus 4, that's reduced as well. So the one that shows oxidation is C. Now let's move down to number 14. The second ionization energy of calcium is 1150 kilojoule per mole. Which of the following equations represents this statement? Now, for the first ionization energy, what you would have is calcium gas. Oh my god. Giving this Ca plus ion, in its gaseous state, plus 1 electron. For the second ionization energy, you'd have Ca gas, Ca2 plus in its gaseous form, plus 2 electrons. And to remove the electron, the reaction is exothermic. So the answer for this would be Ca plus gas, C. Because you'd be removing another electron from an ion that whose atom had an electron removed previously. That's why it's the second ionization energy and not the first. Now 15, when magnesium metal reacts with dilute nitric acid, 0.512 moles of hydrogen gas is produced. The volume that this gas would occupy at 298 Kelvin and 196 kilopascal when R is equal to 8.31 joule per Kelvin per mole is. You want to use this equation. P is equal to the number of moles, which we call N sometimes, RT. Therefore, volume would be equal to P. Volume would be equal to the number of moles times R times T, temperature in Kelvin, of course, divided by the pressure as is. So what you'd want to put into your calculator is 0.512 times 8.31 times the temperature, 298 Kelvin, which is 25 degrees Celsius, but you want to put your temperature in Kelvin, over 196 kilopascals. Alright, and that should give you your answer, which is 512 times what? 8.31. I am not using this calculator, right? 298 all over 196 and 6.46 or 689. So the closest answer would be B, 6.46 decimeter cube. And let's go down to this. Number 16. Item 16 refers to the following table, which shows the rate results for the reaction A plus B yields C. What is the overall reaction of the order of the reaction? The overall order of the reaction. To find this out, you would have to add the order of the reactions with respect to each reactant. So let's work those out first. Let's work out the order of the reaction with respect to A first. Now, looking at A, you want to look at B and find out where it is, the concentration is constant, right? So here, 0.2 to 0.2. So now, when you look at 0.1 to 0.2, you want to look at it and find out by what factor does the rate increase or decrease. In this case, the rate is increasing by 2, so it doubles. If you're not sure how to look at it and get this, what you want to do is divide the second number by the first number. So you can say 0.2 over 0.1, and you would get 2. Now you want to say 2 to what power will cause here, what happens to the rate of the reaction here? 0.0061. I'm sure it doubles, but let's look. Over 0.0032. So it increases by a factor of 2. So 2 to what power gives you 2? And for this, it is x would be equal to 1. Therefore, the order of the reaction with respect to A is first order. Now do the same for B. Look at A, find out where it's constant. Here, you can see it doubles. So 2 to the x is equal to, it doesn't change, so 1. 2 to what power is equal to 1? And let's change the variable to y. Y in this case is 0. Therefore, the order of the reaction with respect to B is 0 order. So 0 order and first order. So the overall order of the reaction is 1 plus 0, which is 1. So the overall order of the reaction is first order. Number 17. Which of the following phrases does not define the rate of a chemical reaction? The rate of a chemical reaction speaks to how quickly, or the rate at which, or the speed with which the products are formed, the reactants disappear, or the change or the concentration of both the reactants and product change. So A says the rate of formation of products. That can be used to define the rate of reaction. B says the rate of consumption of a reactant. That sounds feasible. C says the rate of consumption of a product. No, that sounds kind of weird to me because products aren't consumed. Unless it's a reverse, let's not go there. Now, the change in concentration of the products with respect to time, and that's most definitely it. So 17 is C. Number 18. John plans to measure the rate of reaction between calcium carbonate and dilute hydrochloric acid. It's important for you to know the products formed when a carbonate reacts with an acid, and you would get a salt, CO2, and water. Which of the following setup of apparatus is most suitable for this investigation? And looking at these, you would want to use B so that you can calculate the volume of CO2 produced in the syringe. Okay, that's fair enough. Number 19. A buffer is made by dissolving 2.8 grams of sodium benzoate in 1 dm cube of 0.4 mole per dm cube of benzoic acid. The Ka, or the acid dissociation constant of benzoic acid, is 6.4 times 10 to the minus 5 moles per dm cube. The pH of the buffer is fancy. Alright, first the pH of a buffer, BUFFER, is equal to pKa plus log to the base 10, of course, of the concentration of the salt divided by the concentration of the acid, represented by Ha, however you want to represent it. Now, we know the concentration of benzoic acid, however, we do not know pKa, but we can work that out because pKa is minus log to the base 10 of Ka, so that is equal to pKa. And we know the mass of sodium benzoate used, so we can find out the number of moles and thus calculate the concentration. So we're going to do that first. So we know that 1 mole of sodium benzoate is equal to 12 times 7 carbons plus 5 hydrogens plus 2 times 16 for oxygen, and 23, which is for sodium. And you want to put that into your calculator. So 12 times 7 plus 5 plus 2 times 16 added to 23, and you should get 144. At least that's what my calculator told me. So 144 is for 1 mole of sodium benzoate. So how much would 28.8 grams give you as per the number of moles? What you want to do is cross multiply, so you'd end up with 144 times the unknown number of moles being equal to 28.8 grams. Divide through on both sides by 144, and what you would get is 28.8 over 144 is 0.2. So the number of moles is equal to 0.2. Now, it's 1 dm cube, therefore the concentration for the salt would be 0.2 mole per dm cube, which could be represented by big M, which is molar. and we know that the concentration of the acid is 0.4 moles per dm cube as well, and pKa is equal to minus log to the base 10 of Ka, which we got to be 6.4 times 10 to the minus 5. And I am going to put all of that into the calculator, but if you don't want to, I got 4.19 with a lot of other numbers, but I'm going to put everything into the calculator. So the pH is therefore equal to minus log to the base 10 of 6.4 times 10 to the minus 5 moles per dm cube. I'm going to leave out the units for now because it's a bit hectic to put units. Log to the concentration of times the concentration of what? The salt, which is 0.2 molar, over 0.4, which is the concentration of the acid, and therefore the pH of the buffer is equal to plus the log to the base 10 of 0.2 over 0.4. I got 3.89, which is 3.9. And let's look at the options. Okay, so in the calculator you got 3.89. So we're looking for an answer resembling that. So 2.3 is not it. 2.9 is definitely not it. 3.2 is not it. But 3.9, 3.89 rounded to the nearest tenth is 3.9. Okay, fair enough. The solubility product of barium sulfate at 25 degrees Celsius is 1 times 10 to the minus 10 moles squared per dm to the minus 6. Now the number of moles of barium sulfate that will dissolve in 1 decimeter cube of water to form a saturated solution is... Okay, this one is quite simple. What you want to do is just find the square root of 1 times 10 to the minus 10 moles squared per dm to the minus 6, and you would get 1 times 10 to the minus 10, and then the square root of that would give you 1 times 10 to the minus 5 moles per dissolved in 1 dm cube. Okay, so your answer for this is C. Now number 21. What effect does a catalyst have on a chemical reaction? The activation energy is lowered, the rate of reaction is doubled, the rate of the reaction is decreased, the catalyst is consumed in the reaction. No. This one is definitely not true. So D is definitely not true. There's no way to tell if it's actually doubled, so that's kind of vague. And the rate of the reaction is decreased. Now, the aim of a catalyst is to increase the rate of the reaction, but there are some catalysts that do decrease the speed of the reaction or the rate of the reaction. But the effect of the catalyst, or the main mode of action, is to lower the activation energy in order to create an alternative pathway for the reaction to proceed. Now 22. Compounds P, Q, and R form an equilibrium as shown below. So 2P aqueous plus a mole of Q in its aqueous state forward yields 2R, and then there is a backward reaction, so the equilibrium is represented as such. Okay, so the units for the equilibrium constant Kc, you have to use all the things in the aqueous state. What you'd find is you would have, I decided to bring this over a bit because it was going to get a bit bulky, but here we have R, and Kc is equal to the product of the concentration of the products, right, divided by the product of the concentration of the reactants. So what we would get is mole per dm cubed for R squared divided by mole per dm cubed for P squared times mole per dm cube for Q. Okay, and if you actually write that out by removing the squares and using actual expanded variables, you would have mole squared dm to the minus 6 all over mole cubed times dm to the minus 9, and mole squared would cancel this and leave you with 1 mole, and minus 6 would cancel, leaving you with minus 3. So what you would end up with is, seeing that mole is on the bottom, you'd end up with per mole, and seeing that per dm cube is on the bottom as well, you'd end up with dm cube instead, so the inverse. So your oh my god, what is it called, units would be per dm cube per mole or per mole dm cube, whichever one you want to say. So dm cube per mole is B, letter B, not number B, but letter B. Now, what would be the expression for the solubility product KSP of lead iodide? Now, the formula for lead iodide is PbI2. So, therefore, you would have that separated into what? Pb2 plus ions and 2I minus ions. So the KSP would be equal to the concentration of Pb2 plus ions times the concentration of the I minus ions squared. Now, seeing that this has the Pb2 plus ions squared, that's not correct. Now, this seems correct, but it's always good to check. And the 2 is not supposed to be in here, so those are incorrect. So the answer for this is B. And 24 says, which of the following statements does not refer to a system in dynamic equilibrium? Okay, so A, 24, which of the following statements does not, pay attention to the not, refer to a system in dynamic equilibrium? A, the reaction is reversible. B, the amounts of all the species in the system remain constant. Well, that's true, but this needs a bit of thinking, because C says the concentration of all reactants and products are equal, while D says the rate of the forward reaction is equal to the rate of the backward reaction. Now, this is correct undoubtedly, but B and C kind of confusing my brain. Now, B says the amount of all the species in the system remains constant. Now, that's true. Now, this says the concentration of all reactants and products are equal. The reason why this is not true is if it were true, then the equilibrium constant would always be 1. Let me show you. So the concentration of all the reactants and products are equal. If the concentration of the reactant is 0.1 molar, while the concentration of the products is the same, which is 0.1, remember that the Kc is equal to the concentration, or the product of the concentration of the products over the products of the concentration of the reactants. So if that's 0.1 and that's 0.1 as well, Kc is equal to 1. And if the concentration of the products had amount to 0.5 and the the reactants are equal, then it would be 0.1 as well. It would be 1 as well. So Kc would always be 1, and that's not true. So the answer for 24 is C. Now 25. Item 25 refers to the following cell diagram, right? So we can see that zinc here is oxidized, so this is the anode, and copper is reduced, so this is the cathode. Now, which of the following conditions will cause an increase in the cell potential? A. Increasing the concentration of zinc 2+ ions only. B. By decreasing the concentration of the Cu2+ ions only. C. By adding NaOH to the Cu2+ solution and increasing the concentration of the Zn2+ ions. Or D. By decreasing the concentration of the Zn2+ aqueous ions and increasing the concentration of the Cu2+ ions. What you'd want to do is decrease the concentration of the Zn2+ ions while you would increase the concentration of the Cu2+ ions. 26. Which of the following pairs of substances would make a good buffer? Good buffer is made from a weak base and the salt of that weak acid, and the salt of the weak acid. Or a weak base and the salt of the weak base. So it depends on if it's an acidic buffer or an alkaline buffer. In this case, looks like HCl is a strong acid, so this is out of the picture. HCl is a strong acid. Now ammonia, and we need the salt of this ammonia. So it cannot be sodium nitrate, so the answer here is incorrect. So ammonium chloride would be a salt of it, so answer is C. During a chemical reaction, disproportionation is said to occur if a substance undergoes oxidation but not reduction. Nope. Undergoes reduction but not oxidation. No, it actually undergoes both. So acts as an oxidizing agent but not a reducing agent. That's not true either. So we're left with D, which acts as both an oxidizing and reducing agent, and that's the correct answer. Now 28, which of the potential for a cell, what is the potential for a cell with the following reaction? Now Zn0 but 2+, so that is oxidized, so that's the anode, and Br, but this is -2, so this is reduced, so Br is at the cathode, and the cell potential is equal to the cathode minus the anode. So what we need to do is refer to our data booklets to find out the E0 values for these. For zinc, the E0 value, Zn, let's just put that there for now, is -0.76, and for bromine, it is 1 point, that's a positive, plus 1.07, okay? So therefore, you want to put the numbers in the equation as is. So we established that the bromine would have been the cathode, so it's plus 1.07 minus the anode, which is minus 0.76. Let's move that down a bit. I accidentally clicked. Okay. So the answer for this would be D. Now let's look at 29. The value of Kc for the equilibrium here would be, and seeing that these are gases, you're going to use the partial pressure. Okay, needed space. So what you would find out is that for this you would find that the partial pressure of HI squared over the partial pressure of the H2 gas times the partial pressure of the I2 gas was equal to 860. Now, looking at this equation, you can see that everything was halved, right? So what you would end up with is half the concentration, the partial pressure, sorry, of HI over half the concentration, the partial pressure of H2 times half the partial pressure of I2. This would leave you with the partial pressure original, which is 860, decreasing by 2, decreasing by a factor of 2, and increasing by a factor of 4. So you want to divide 860 by 2 and multiply it by 4. You would end up 2 into 2, 124, 2 with 860 times 2, which is 1720, being the new equilibrium constant. So your answer for this would be D. Now let's move to 30. Number 30, the standard electrode potential for tin is minus 0.14 volts. Now, in which of the following equations is the metal unable to reduce tin? So what you want to do is subtract, or not subtract, but the cathode minus the anode, where you will keep the tin here as being unable to reduce tin. That means that tin is being reduced. Keep tin as the here cathode, the one being reduced. So minus 0.14 minus 2.38. That's not correct. Okay, yes, it's correct. So what you want to do is put this into your calculator. Minus 0.14 volts minus 2.38. If your value is positive, that means that the reaction is feasible, therefore this electrode has the potential to reduce tin. So 0 minus 0.14 minus negative 2.38 gives a positive 2.24, therefore that reaction is feasible and magnesium can reduce tin. Now minus 0.14 minus negative 0.44 would give you a positive 0.3, and that tells you that iron can indeed reduce tin because the reaction is feasible. Now 0 minus 0.14 minus negative 0.76 gives positive 0.62, therefore the reaction is feasible and the zinc can reduce tin. Now the last one, which is the answer, 0.14 minus 0.13 gives you a negative minus 0.01, therefore the reaction is not feasible, and thus lead here is not able to reduce tin. Therefore, that's the answer, unable to reduce tin. Now 31, which of the following statements about bromine is correct? And this says it is red-brown in color. Yes, it is. It is denser than chlorine, is it? Now the density of halides or halogen or the halogens, they increase as you go down the group. That's why it's assumed that astatine is actually solid. Now if bromine is below chlorine, then of course it is denser than chlorine. Yes, and chlorine is 17, bromine is 35, it is indeed below it, therefore denser. Now bromine is a gas at room temperature and pressure. Nope. If you've seen bromine, it is a liquid. Okay. So I and I only. And 32. Which of the following oxides of elements in period 3 are correctly matched with their acid-base character? Now aluminum oxide, it's amphoteric, so it can show both basic and acidic properties. Sodium oxide, no, that's ionic-ish. Yes, ionic, so it has basic properties. And phosphorus 5 oxide, that has acidic properties, so this is correct as well. So all three, 1, 2, and 3. Now 33. Which of the following elements reacts slowly with cold water and burns with a bright white flame? And that is magnesium. Calcium carbonate decomposes at a lower temperature than barium carbonate because calcium oxide is less stable than barium oxide. The calcium ion is larger than the barium ion, The standard enthalpy of formation of calcium ion is less negative than that of the barium oxide. The lattice energy of calcium oxide is larger than that of barium oxide. Okay, so let's look at these, starting from D going up. So this says that the lattice energy of calcium oxide is larger than that of barium oxide, and that wouldn't be the reason why calcium carbonate decomposes at a lower temperature than barium carbonate, because if the calcium oxide lattice energy is indeed larger, that means that it would have stronger bonds, then would require more energy to break those bonds. So that would mean that by right, barium carbonate or barium carbonate would be the one with the lower temperature at which it decomposes, and that's not what the question says. Now the standard enthalpy of formation of calcium oxide is less negative than that of barium oxide. That's not true. Barium oxide is less negative than calcium oxide. And this says the calcium ion is larger than the barium ion, and that's simply not true. Now calcium oxide is less stable than barium oxide, and that is true, and that would really explain why calcium carbonate would decompose at a lower temperature than barium oxide, because seeing that barium oxide would be the more stable one, it would actually want to maintain itself and not change, so it would be more likely the one to resist the change of the thermal decomposition, and therefore calcium oxide would be more susceptible to thermal decomposition. So the answer for 34 is A. And 35, which of the following properties belong to group 2 elements on the periodic table? High melting point, low density doesn't seem right to me. Low densities, nope. Poor electrical conductivities, no. They are actually good conductors because they're metals. So low melting points, no, they have high melting points. And poor electrical conductivities, no, as I said, they're good conductors. So high melting points and high electrical conductivity seems like the answer to me. 36. The insolubilities of the group 2 sulfates make them very useful in diagnostic medicine because they appear opaque on X-rays. Which sulfate is most commonly used for X-rays? And that's barium sulfate. Just know this by heart. Now, silicon carbide has a structure similar to that of diamond. What are the advantages derived from using silicon carbide ceramics when compared with steel? Silicon carbide is more resistant to oxidation. Sounds like an advantage to me. Silicon carbide has a higher melting point. Also seems like an advantage. Silicon carbide is less likely to deform under compression. That's also one. So 37D. 38. Which of the following transition element has an unpaired electron in it in an s orbital? And this kind of sounds weird, but you should know the exceptions. It's chromium and copper. So these are the two exceptions, because a half-filled or a filled d orbital is more stable. So what would happen is one of the electrons would, instead of going to the 4s, it would just jump into the 3d to finish filling it halfly. I just said filling it halfly or filling it completely. So that's the exception. So for both copper and chromium, there is only one electron in the 4s orbital. So there you go. Now 39 refers to the following graph, which shows the first ionization energy of some elements, and these seem to be the first row transition elements along with calcium. Now the sharp increase from copper to zinc is caused by filled 4s orbitals. Now the reason why I didn't even consider any of the others is because they introduced the 4d orbitals in all of them. So I didn't have to think much about it, because 4d orbitals have nothing to do with the first row transition elements, because the first row transition elements have 3d orbitals, and the second row of the transition elements are the ones that have 4d orbitals, which are not a part of your syllabus. So yeah. 40. Items 40 to 41 refers to the following properties of 4 oxides labeled A, B, C, and D. Alright? Now 40. Which of the following, or which I need to stop this. I'm not reading properly. Which of the oxides is an oxide of silicon? Now silicon, most likely it would be silicon dioxide, and that's a giant covalent structure, and it has neutral to basic properties, so about pH of 7 to or higher, I should say. So the answer for this is B. Yes, giant covalent. And there we go with the pH. Now the oxide of sulfur would be most likely be sulfur dioxide, and that's a gas. And seeing that there's only one gas, it's D. And the gas is also acidic. Yup. And it's a covalent molecular structure. Okay, so this requires us to match each of the cations below with their either precipitate A, B, C, or D in the reaction scheme that is located above. Now first, they want us to locate the lead 2+ ions, and the conformation for the lead 2+ ion would be D, because here we have white precipitate forming insoluble in excess. So this could either be aluminum or lead, but what aluminum 3+ or lead 2+, but what confirms the lead is the yellow precipitate formed when you react it with potassium iodide, and what would form is PbI2, which is lead iodide, and that is actually yellow. All right, Now for the Zn2 plus, the zinc, this would be a white precipitate when ammonia is added in excess and it's soluble. So this would be A. And PB, or as I said, we didn't know, so that would be B. Alright, so now we're at 45 and then we'll be done. I'm trying to find a way to make these shorter. Like, these are 1 hour videos and ain't nobody want to sit for 1 hour. So what deduction can be made? This was the last question on the 2017 paper, and chances are I'm going to do the 2018 paper very soon, and if it is the last question on the 2018 paper, I kid you not, I would not be surprised. So what deduction can be made from the following reactions of iodine and chlorine with sodium thiosulfate? Now, based on the reactions, we can see that iodine here was reduced to minus, alright, and chlorine here was also reduced. Okay, so both halides are oxidizing agents because they were reduced. Now, both chlorine and iodine are not oxidizing agents. No, they are oxidizing agents. Both chlorine and iodine show the same oxidizing power. No, because this is -2 and this is -8. No, iodine is a stronger oxidizing agent than chlorine. No, this is -2 and this is I'm sure 8 is a bigger number. So I think not. No, chlorine is a stronger oxidizing agent than iodine, and yeah, I think this is fair. Mainly because this went to -8 versus this going to -2. So that was the paper. And as usual, if you're hearing this, that means you've made it to the end of the video. You know what to do, drop a like, subscribe, comment, of course, and don't be afraid. I almost said don't feel free. Don't be afraid to reach out to me on Instagram at young_genius.official or on my personal @cam_EO. My name is Camille, by the way. Yes. And as usual, guys, you know how the thing's set. You know you must dream big and don't forget to do that. I dare you. So until next time, bye guys.